So the second part of the investigating rates called practical is it uses a precipitation reaction. A precipitation reaction is a reaction that produces a colour precipitate. In this case, you get a white precipitate forming, and it uses what we're going to investigate is we're going to investigate the effect of temperature on how quickly that reaction goes. And we're going to measure how quickly the reaction goes by measuring how quickly a cross disappears, because we can't see the cross because it's obscured by the white precipitate. So very briefly, the equipment that you need. The two reagents or reactants are hydrochloric acid, is one of them, and sodium thiosulfate. And if you add those two together, you get a precipitate of sulfur actually that's formed. Now, you don't need to know the chemistry of that reaction. It's quite complicated, but all you need to know is that you've got those two reagents. What you need to do is you need to warm them up in a water bath. So you've got a water bath that you're going to have at different temperatures, and we're going to use 4 different temperatures: 20, 30, 40 and 50 degrees C. And the reaction is really quite simple. The first thing that you need to do is that you need to get your two reagents and equilibrate them, so you get them both up to the same temperature, the temperature of the water bath, be that 20, 30, 40 or 50 degrees, and then just add the two reactants together with your flask over a cross, and the precipitate will form, and at a certain point in time enough precipitate is formed that you can't see the cross. Now, how quickly the cross disappears is an indication of the rate of the reaction. The quicker the cross disappears, the quicker the rate of the reaction. The longer the cross takes to disappear, the slower the rate of the reaction. So this video shows the two solutions which have been equilibrated to the right temperature being taken out of the water bath and added together in a flask, and then we're going to video the cross disappearing. Obviously the reaction is going on all of the time, and the precipitate will form, and at a certain time there'll be enough precipitate that you can't see the cross. Now, the key thing here is that the rate of the reaction, the time that it takes for the cross to disappear, is inversely proportional to the rate of the reaction. So if the time for the cross to disappear is short, then the rate is high. If the time is long, then the rate is low. So it's an inversely proportional relationship between the time and the rate of the reaction.
Wait, you can still see it.
Yeah.
No. Still there. No, has it. Can you stop a minute? You can see the subjectivity there about. Yeah.
So what we're going to do that experiment, and we're going to do it at 4 different temperatures: 20, 30, 40 and 50 degrees C. So in the experiment, we're going to change the temperature. So our independent variable is the temperature. And we're going to keep everything else the same. We're going to use the same reactants, the same concentrations and the same volumes. And we're just going to change the temperature that we do the reaction at, and we're going to time how long it takes for the cross to disappear. Now what you see is this relationship, whereas the temperature increases, then the time for the cross to disappear decreases, and the key thing here is to note that the rate of the reaction is proportional to 1 over the time. It's inversely proportional. So if I calculate 1 over time, then I get a relationship that is increase in temperature increases the rate of the reaction. And that's what we see, we know that temperature does in fact increase rate of reaction, and therefore it decreases the time taken. Now, that's a simple relationship. What we have to get to is a more complex relationship, and as a rule of thumb, we use this relationship here. Every 10 degrees C increase in temperature doubles the rate of reaction, and if we plot our results on a graph, we can see that on the next slide. So this graph shows the temperature along the bottom. I've got more or less 20, 30, 40 and 50 degrees C, and 1 over the time taken, the rate of the reaction up the side. Now, the thing to notice is that it's not a straight line relationship. It's a curved relationship, and that curve is because a small increase in temperature results in a more than linear increase in the rate of the reaction. Now, we'll look at that when we do the theory, the collision theory, to explain this. But the key thing is a 10-degree increase in temperature doubles the rate of reaction, and that the temperature has more of an effect on the rate than concentration. Concentration was a straight line, whereas temperature is a curve, because temperature has an increase effect on the rate of reaction. A small increase in temperature results in a big increase in rate of reaction. Now, in the same way that we accounted for the change in rate with concentration and with particle size using collision theory, we can use collision theory to explain why temperature affects rate of reaction. Now, we said before that in order for a reaction to happen, two particles need to collide, they need to hit each other with enough energy. That's the key thing, with enough energy. Now, what happens if you heat a solution up is I'm going to have the same number of particles. I'm going to have, at an increased temperature, I'm going to have the same number of particles. I haven't changed the concentration, so I've got the same number of particles. These particles are moving much faster. They've all got higher kinetic energy. Now, if those particles are moving around with higher kinetic energy, two things are going to happen. They're going to collide more frequently, so more often, but they're also going to collide with higher energy. Now, that accounts for why we get this double whammy effect, this increase, this large increase in rate of reaction with temperature, because there's two things happening. The particles are colliding more often and they're colliding more frequently. And therefore, I'm going to get more frequent successful collisions that are going to result in the reaction happening. So I get a much faster rate of reaction with temperature. Right, to show that we've understood that, we're just going to have a go at a quick exam question. It says, a student investigated the rate of reaction. The student investigated the reaction between zinc and dilute sulfuric acid. The products are zinc sulfate, and it gives you the formula of zinc sulfate, so NaSO4, and hydrogen. Write a balanced equation for this reaction. Well, they've given us quite a lot of information in there, but basically it's MASH, isn't it? Metal plus acid gives salt plus hydrogen. So the metal is zinc, and it said a balanced symbol equation. So zinc is Zn. I'm going to put state symbols in, why not? Zinc solid plus it's sulfuric acid, dilute sulfuric acid. Now I need to know the formula of sulfuric acid. Sulfuric acid is hydrogen sulfate. 2 hydrogens go around with sulfate because sulfate is 2 minus. H2SO4 is sulfuric acid. That's going to be AQ. And it's going to make zinc sulfate, ZnSO4AQ, because it's soluble, and hydrogen H2 gas. Quite an easy 2 marks really, because the formula of the salt is given in the question, and it is actually balanced. There's no balancing that needs doing there. It then goes on and says, a student carried out 2 experiments. The same mass of zinc and the same size pieces of zinc were used in each experiment. The results are shown in the table. So I look at the table, and what he's done is, with the same amount of zinc and the same size zinc, that he's done the experiment at different concentrations. 0.5 and 1.5, and he's also done it at different temperatures at 20 degrees C and 40 degrees C. So he's done what you shouldn't do in experiments. He's changed two things. He's changed both the concentration and the temperature, and they've both increased between the first experiment and the second experiment. Now, he hasn't actually measured the rate of reaction. All he's recorded is the fact that the reaction goes slowly at low concentration and low temperature, and it goes quickly at high concentration and high temperature. Now, that's what I can get from his results. It says, evaluate these results, explaining the reasons why the rate of reaction in experiment 2 is faster than the rate of reaction in experiment 1. In your answer, you should refer to the frequency and energy of collisions between particles. Now, the basics of this is to say that the concentration has increased. That's going to increase the frequency of collisions because I've got more particles per unit volume, and I'm going to have more collisions because of the increase in concentration, or I'm going to have a greater frequency of collisions because of the increase in concentration. The temperature has gone up, so as well as having more frequent collisions because of the rise in temperature, I'm also going to have more energetic collisions because of the rise in temperature. So I'm going to structure my answer in two ways. I'm going to say concentration for first of all. So experiment 2 is increase in concentration, more particles per unit volume. If I've got more particles, I'm going to have more frequent collisions, which means greater rate of reaction. And then temperature in experiment 2, higher temperature means particles move faster and with more energy. This implies that you get more frequent and more energetic collisions, which implies that greater rate of reaction. Now the last little bit is that I'm just going to say that the temperature has more of an effect than concentration. And there I've got a 20 degree increase in temperature, and that is going to quadruple rate of reaction. So I think what I've done there is I've explained that both the concentration and the temperature are going to result in a faster rate of reaction, but the temperature has more of an effect because I get this double whammy of particles colliding more frequently and with more energy with temperature.